All right, so for posterity, for the video part that we'll be watching later, so this will be part one of the final exam review in the spring semester of 2024. All right, and we're starting with a quick review on polar coordinates. So as I was just going over, this blue point A right there in polar coordinates is at a coordinate point of 5, pi over 6. 5 because it's 5 away from the origin. Just count 5 circles out from the origin to get to point A. And it's at an angle of pi over 6. So I count to the second tick mark, it's 2 pi over 12. And that reduces to pi over 6. If I were to try that example on another one, how about point B? I need to count all of the angles around to where B is, looking at those radially outward lines. I count all the way out to 8 pi over 12, or 8 radial lines from standard position, which is still at theta equals 0. So I count 8 of them over to 8 pi over 12. That simplifies to 2 pi over 3. And then count the circles out from the origin to get to the point where B is 4 away from the origin. It's at a distance of 4. So I've got it listed down right here. 4, 2 pi over 3. Then there's a whole bunch of stuff with negative angles. Probably I'll get more into that when we actually look at the practice final. But effectively a negative R value here. If I have so negative R, or an R value that is negative, that means I'm going to be going backwards through the origin instead of forwards. So if I come back up and look at these points one more time, and let's bring up our ruler real quick, because that'll probably be helpful to illustrate my point. Set it to 30 degrees and see how accurate this diagram is. It's close, but it's not perfect. All right. So on screen, I've got my ruler that's going through at an angle of pi over 6, or at least close enough to it. Let's set it back to 30 degrees so it is for real. Oh no, it's actually coming through pretty nice. I'm looking at the bigger screen. So, right, an angle of pi over 6. If I draw that line in space, because now lines in polar coordinates, lines like we're used to, like y equals mx plus b, lines will instead have the equation theta equals a number, like theta equals pi over 6. I get this line in space, which definitely covers an angle of pi over 6, where my point A is. But the line theta equals pi over 6 is the same line as theta equals 7 pi over 6. The one that goes backwards through the origin. Right? One of them moves in the positive direction, the other kind of goes in a negative direction. Go with some orientation on the way that these angles work. Which means that I can express point A, one right here, either using an angle of pi over 6 or with 7 pi over 6. Both will get me onto this same line. So then my R value, no, R's absolute value has to be 5, so that's how far away from the origin it is. But R could either be positive or negative. Right, so R is going to be positive 5 if my angle is pi over 6. So I pick my direction and then I want to go forward 5 in order to get there. Or if my angle were 7 pi over 6, I would now have to go backwards along that angle in order to find my point. So I could use theta equal to 7 pi over 6, but then have R equal to negative 5 to go backward to find that point A. And that is the other half of what's expressed down here. So the point A, or the 2 points, 5, pi over 6, and negative 5, 7 pi over 6, are both describing the same point in polar coordinates. Which makes things get a little tricky, because when we're in rectangular coordinates, a coordinate point is always unique. There's always a single x value and a single y value that talks about a point in space. Polar coordinates lose that uniqueness. which is not something we should be too surprised by at this point, because we've seen a whole bunch of that stuff come up with like the inverse trig functions. And they're kind of a pain because of how not unique values off the unit circle are. So generally what we'll do then, since these points aren't unique, is we'll set restrictions on R and theta to make sure that we talk about a unique point. And the easiest way to do that is to stick to only positive values for R and only standard unit circle values for theta. So things between 0 and 2 pi. I want to simplify my angle so that it's less than 360 degrees, but still positive, or less than 2 pi radians. I can always find a coterminal angle to talk about instead. So the most standard way to express points in polar coordinates is that guy right there. Positive R and theta between 0 and 2 pi. Probably if you were to guess to what standard was, that'd be your guess. Let's see, there's probably a bunch of other stuff in here. Figuring out where points are. Is this the same question? No, it's the next one. But yep, same thing. We're locating some points. Here we're gonna switch from R and theta to X and Y, which means we should get some equations for transferring between polar coordinates and rectangular coordinates. Easiest way to do that are these two equations on screen. X is R cosine theta and Y is R sine theta. Very, very similar to what we're used to from the unit circle, because again, the unit circle just is polar coordinates, but specifically with R equal to 1. The radius of the unit circle is 1. So again, if R is 1, then we just go back to X equals cosine theta, Y equals sine theta, exactly the same definitions we're used to from the unit circle. We're just expanding those to any size circle we want, instead of just the unit circle. We just multiply sine theta and cosine theta by R. That lets us switch between the two systems. So in addition to those equations, we ought to have a couple more on here. Yeah, here they are. So in addition to X equals R cosine theta and Y equals R sine theta, we've got two more equations that spring naturally from that. That's easier to use if I've got to go from X and Y to polar coordinates. But they are the Pythagorean theorem and the definition of tangent. Those are the equations we use. X squared plus Y squared is equal to R squared. That is just the Pythagorean theorem. Same one we've been using the whole time, but now we're going to adapt it to polar coordinates. So we can use that equation to figure out what R is. Anytime we need to know theta, if we start from X and Y, well, we'll know that tangent of theta is equal to Y over X. Now, we should be careful that we specifically use this equation, tangent theta equals Y over X, to be our transition between rectangular coordinates and polar coordinates. So we've talked about the inverse trig functions enough, but it's time to bring it up one more time. A lot of people like to simplify this equation to theta equals the tangent inverse of Y over X. And that is not necessarily true. It's not always correct. Remember that the tangent inverse function has a very restricted range. It can only give us answers in the first and the fourth quadrants. So theta equals tan inverse of Y over X, not a great equation to start with. We might use that in the process of figuring out theta, but it's not an equation we need to start out at. So we've got to keep tangent theta equals Y over X. Hopefully we've done that enough. Okay, cool. Come on, scroll down. There's some other stuff on here. Okay, yep, it's so convert theta equals pi over 6 into rectangular form. Again, it should look like a line. We talked about that earlier. Here's an old triangle problem. And I think we'll see something just like this in the practice final. So now that I've delayed the start of the practice final for a good like 10 minutes, some of that was even on video. Let's take it to that part. Where did I put my pen? Here it is. All right, the practice final in earnest. So you can find it in the usual spot in the notes. Just put it with all the other practice exams. And let's go ahead and get through as much of it as we can. As I said at the beginning of the video and elaborated on even before I started recording, this is probably going to be a 3-part review as far as all the videos that come together. So one today, one Wednesday, and a third one TBD. We'll cover anything that I don't get all the way through in lecture in recitation this week. Since we don't have a quiz or an exam, we'll use that time for review. So let's go through this problem. Okay, so the exact value of the tangent of pi over 6 is one of the following. And might as well use this moment to remind ourselves what exact value means. So remember that an exact value is one that expresses irrational numbers in their irrational form, right? So the square root of 3 is an irrational number, so we just write down square root of 3. Pi is a rational number, so we just write pi as its exact value. 3.14159 is a very good approximation for pi, is not an exact value. It's a decimal approximation. So we have exact values versus decimal approximations. So right off the bat, without thinking at all, I'm going to get rid of those two answers, E and F, because both of those are not exact. Because again, they are decimal approximations. So I know I don't want to pick either one of those. I instead want to pick the value of tangent pi over 6 in its exact form. And if we recall back to the unit circle, tangent of pi over 6, well, 6 is 3 plus 3. There are 2 3s in 6. So there are 2 3s in the answer. 3 over 3. But hopefully that question is very quick when we take the final. We're expecting that to be you look at it, it's something you know from the unit circle, should hopefully be committed to memory by this point, but I know that sometimes that stuff leaks out. But again, we expect that problem to go very quickly on the exam. So if it's not that quick, I'd suggest reviewing the what is it? The unit circle practice quiz, the one that we've got on there. Got a shot. I may even post a new version of that quiz just for some extra review. But okay, number 2, the exact value of the sine inverse of -1/2. Well, if we think about the unit circle, we might go to figuring out where sine is equal to -1/2. And from the standard version of the unit circle, sine is -1/2 at 7 pi over 6 and 11 pi over 6. But both of those are incorrect answers. Oh, I didn't even put 7 pi over 6 on there. Because it is the inverse function, I have to pick the answer that the inverse function will give, which is not 11 pi over 6, but is instead negative pi over 6. Those two are coterminal angles. Let's try again. Those two are coterminal angles, but only one of those is an answer that sine inverse will give us. So make sure you pick the appropriate one. This case being negative pi over 6. All right. This next one for tangent equals x plus pi over 3 I'm gonna set this one up just for fun. This should be x plus pi over 3 is equal to pi over 2 plus k pi. I'd solve that thing for x, I'd pick out the first couple of asymptotes, and I'll get that the answer is E. It's those two, if you solve that too. Now, this thing is off worksheet 8. Worksheet 8. Which we did not cover in depth this semester. I left the lessons on V2L if you want to check it out. The asymptotes are the single most important thing out of that section. But worksheet 8 is not going to appear on the final exam, nor was it on any quiz or exam we've taken so far. So you do not need to know how to do this problem for the final. So let me write that in somewhere else. Not in spring 2024. That's us. So we don't need to know that problem. But just in case you wanted to know that problem, the answer is E. And perfect. We get to go convert the rectangular coordinates, 3, -3, into polar coordinates. So let's go figure out where these points are. So if I notice, coming through this bit, some similarities in all of the answers, I've got every R value is some permutation of square root of 3 times the square root of 2. So all my R's must be that, or it's none of these, but quick pro tip, the answer is never none of these. That answer is only on the multiple choice bank in case someone, definitely not me, makes a mistake while writing the question, that none of these is just there to bail me out. None of the questions will be written with that as the intended answer. So don't pick F. It's never good. It's never F. So must be R is 3 times the square root of 2, or maybe -3 times the square root of 2. And all of the angles are some version of a pi over 4. So for starters, let's go through and just put all of these angles in the quadrant that they're located in. Just identify where all those are at. And I'm going to skip the one that's negative for now because I want to talk about it at the end. All of the others have positive R values, which just means whatever angle is showing is the angle that it's on. That's the quadrant it's in. So pi over 4 is in quadrant 1. 3 pi over 4 is in quadrant 2. 5 pi over 4 is in quadrant 3. Try to be a little more concise about that. Quadrant 3. And 7 pi over 4. That's quadrant 4. So I have 4 of the 5 points are in 4 different quadrants. And lastly, let's talk about A. So if I can look at point A, which has a negative R value, means we're going to be going backwards along whatever angle we have. And negative pi over 4, which is just an angle I can plot somewhere in space. I would start by going to the 4th quadrant, right? 4th quadrant from your perspective, because that's where negative pi over 4 is. Just go backwards into the 4th quadrant. Now, from that 4th quadrant angle, I am going to go backwards a distance of 3 root 2 instead of forwards. So I'm start by pointing into the 4th quadrant and then going backwards. And if I'm aimed at the 4th quadrant and move backwards, I would move into quadrant 2. So that first point is in quadrant 2 rather than quadrant 4. Quadrant 2 because its R value is negative, despite the fact that its angle is pointed into the 4th quadrant. 2 and 4 are always backwards from each other. 1 and 3. 1 and 3 are always backwards from each other. Well, now that we've said all that, let's go actually look at the point that we're given. I don't really need to know the exact values of x and y in order to figure out what quadrant it is. I just need to know the positive and negative signs on x and y. And on the point that we have 3, -3, x is positive and y is negative. If I have a positive x value and a negative y value, that means I should be going right and down. So that's quadrant 4. Which must mean that E is the correct answer. So I'd arrive there just by looking at the values that are given. The way I'd actually calculate this stuff specifically, I'll be like this. Using my equations for polar coordinates, r squared is x squared plus y squared, which is 3 squared plus -3 squared, comes out to 18. It means that r itself is plus or minus the square root of 18. 18 is 9 times 2. 9 is a square number. So I can simplify that to plus or minus 3 times the square root of 2, which is where that number that I saw in the r position for all of those points is coming from. I'll also go to the equation tangent theta equals y over x, which is -3/3. Write that in a little better. Which simplifies to -1. And again, this is the equation I really want to work with, the one that just says tangent theta equals -1. Rather than saying theta equals tangent inverse of -1, because that won't necessarily be correct. Because if I go to theta equals arctangent of -1, the answer I'd get was -pi/4, but that's not the angle that I end up using to express the point. I use 7pi/4 instead. So just be careful when using any of the inverse functions. That applies anytime you're going to use an inverse trig function. They are very tricky little functions. So you just have to know how to use them. Very good at finding reference angles, less good at finding anything else. But they're great at reference angles. That's why I like them. Cool. But yeah, anyway, so tangent theta is equal to -1. I'm looking at some class of a pi/4 angle, specifically one that's either in quadrant 2 or in quadrant 4, quadrant 2 or 4. So putting it all together, if I use a theta value that is in quadrant 4, like 7pi/4, I would go with a positive r value, positive 3 times the square root of 2. And if I end up using a theta value that's in the second quadrant, something like 3pi/4, then I need to have a negative r value that goes with it, because I need to go backwards, back and forth quadrant. Since all that's complicated, we usually like to set restrictions on our variables for r and theta. And again, those restrictions are positive values for r, and our angle is just somewhere between 0 and 2pi. Rather than a negative angle or something bigger than a circle, we'll just get a coterminal value somewhere between 0 and 2pi. Yeah, okay. So let's take a look at the next one down. I need to find the exact value of cosecant of 7pi/3. So let's start trying to get that. 7pi/3. That angle is bigger than the unit circle. Right? Or well, it's bigger than a circle, I should say, because angles just measure all circles. It's bigger than 6pi/3, which is 2pi. So it's got larger than 2pi. Means I don't know exactly where this thing is immediately. But I know it's an over 3 class of angle. So if I found something coterminal to it, I'd know exactly where to look. So that's going to be my first step. I want a coterminal angle for 7pi/3. Recall that getting a coterminal angle means I'm going to add or subtract a full circle, right? Spin around in a full circle and you end up pointing exactly where you started. In this case, I've got a very large angle, so I'm going to subtract 2 pi. So 7 pi over 3 minus 6 pi over 3 gets me to 1 pi over 3. Cool. So the cosecant of 7 pi over 3 must be the same as the cosecant of 1 pi over 3. Because again, those angles are coterminal. And if you know your cosecant values, 2 root 3 over 3. If you don't know your cosecant values, you'll have to solve for it. So the way I'd go about that, start with cosecant of pi over 3 is equal to 1 over sine pi over 3, which in turn is 1 over the square root of 3 over 2, which is just the reciprocal of root 3 over 2, or 2 over root 3. And then because this thing is a multiple choice exam, you've got to rationalize that value, because I'll be rationalizing when I give you the multiple choice bank. So multiply top and bottom by the square root of 3. And I get 2 root 3 over 3. But again, started with that value from the beginning. 2 root 3 over 3. All right, then a word problem. So we've got a medical helicopter. It's 120 miles due south and 15 miles due east of a hospital. If the pilot wants to travel directly to the hospital, what bearing should be taken? So let's draw a diagram. So I want to start by going 120 miles due south, and then only 15 miles due east. Get a triangle kind of like that. Where I then want to fly from one spot to the other. So up here at the top, crap, I used hospital and helicopter. So both of those want to be H's. Let's use a red cross for the hospital. And I'll call it specifically heli for the helicopter. I want to know the bearing angle from one to the other, knowing that this is 120 miles, this is 15 miles, and I've got a right angle in between them. So I'll probably want compass rose. I'll place it on top of the helicopter. And the helicopter wants to fly from its position back to the hospital. Yeah, so we're going that way. Which means the bearing angle I'm looking for is this one right there. That's the bearing angle that I'm after. I can tell just by the way that the helicopter needs to fly that my bearing should be northwest, That's the direction I'm traveling. So I just need some math to figure out what the value of beta is. A few ways we could do that. I could either come draw the angle right next to the helicopter, but it's on the inside of the triangle. Or I could recognize by opposite interior angles that beta is congruent to that other angle in the upper left corner. Right? Those are opposite interior angles, which makes them congruent. Or I could use the fact that if I'm looking at bearings to or from the same two places, the value of the bearing angle will be the same, whether I'm going to or from. They both have the same bearing angle, but the cardinal directions will be different. So like the bearing that I labeled next to the hospital, going back to the helicopter is southeast, whatever that angle is. And I just want the one that's northwest. But the process for calculating it is the same. I'll set up an equation that looks like tangent beta equals opposite over hypotenuse, which is 15 divided by 120. Which means that beta itself is the arctangent of 15 over 20. Arctan of 15 over 120. Plug that into a calculator and you can get an answer. But since I was super prepared today, I calculated it ahead of time. 7.13 degrees. That's what I got when I plugged it into my calculator. So I'll come search the answer box for a bearing that's got that angle and also goes northwest. And it looks like it's just barely on the edge of the screen. Option D, northwest, 7.13 degrees. All right, up next, let's talk about simple harmonic motion. So recall first that an object is in simple harmonic motion, or motion is simple harmonic. Yeah, motion is simple harmonic if it can be expressed with a single sine or cosine function. So anything that's a sine bx or sine bt or a cosine bt, those are objects in simple harmonic motion. A nice looking periodic sine wave. We call that simple harmonic motion. And that's what we're going to describe here. It gives us the model or the equation of the model. D equals -5 sine of 4 pi t, and wants us to answer two questions in tandem. It wants both the maximum displacement in feet and the frequency and oscillations per second. So just remember that the maximum displacement is the amplitude. So I care about that -5 right there. The amplitude here, which is the absolute value of A, is equal to +5. Up next, I'll go get the period, which is 2 pi over B, which in this case is 4 pi, making that 1/2. And finally, the frequency, the part we're after, is 1 over the period. The 1 over 1/2, and that's 2. So option E, 5 and 2. Be careful of 5 and 1/2 because that's the maximum displacement in the period. And the question was asking for the maximum displacement and the frequency. Cool. And that will conclude part 1 of the final exam review. Stay tuned for part 2.